me start the recording. So today I'm pretty much going over kind of what you need to know in the electrical team. So pretty much like all the work that you're going to be doing throughout the term. So this is our first workshop to go over like kind of the initial stuff that you're going to do, and it also relates to all the electrical stuff that you've been given as a task pretty much. So let me go through that. In the electrical chat, I'm gonna post a link. I'm gonna post a link, and the link pretty much goes through what this workshop's about. So if you ever want to take a look back at what we did, notes are already taken for you, and also a general guideline of what is happening. So I'll post it in the electrical chat. There we go. All right, so let me get started. So first I'm going to do the intro to electrical vehicles pretty much. So how do you turn a normal vehicle into an electrical vehicle? Pretty much what we're trying to do, right? There we go. So pretty much what we're trying to do is turn a normal vehicle into electrical vehicle. So for this example, I'm going to use an electrical bike, but this really applies to pretty much any vehicle. And the fact is, electric vehicles actually are very, very simple and only require 4 main components. So the first component is, let me know if this is big enough, but the first component is something that you need to actually move your electric vehicle. So usually this comes in the form of electric motor, right? So this turns your electrical energy into your kinetic energy, right? So think about your car, right? You have a car engine that lets you go forward. This is the exact same thing. It's an electrical motor. As well, you need some power source for our electrical motor. So usually that comes in the form of battery, which stores electrical energy for us. So here I'm going to draw a little battery. And this pretty much stores charge for us and lets us move forward, right? But unfortunately, we can't just plug our battery straight into our motor and start going forward, right? We need some in-between between the motor and the battery that controls the specific signals that we need to be able to move forward. So for example, if you think of your car, right? Your wheels don't just spin on their own. They need an engine in between. Maybe they have a transmission or a muffler. So this is the in-between for our electrical system. Sorry, let me keep typing. So we have a motor, a battery, and this is called the motor controller. So what the motor controller does is it takes in the power from the battery. So it's going to take power from the battery, and it's going to translate the power into electrical signals that our motor can actually use. So this is the main schematic that or the main circuit that you're going to be designing throughout the term. And let me put like a little sine wave, and this is going to control our motor. So this is the main schematic that we're going to control, and pretty much it tells our motor how to move. And we need a lot of electrical components to be able to do that. There we go. And now we need the last thing, right? How do we go from, we are almost pretty much finished our bike, but how do we tell our bike to go forward, right? So if you think about like a normal bike, usually you have pedals on it that you can just pedal. Or if you think about a car, you have a gas pedal that you press down, and it makes your car go forward. An electric bike will have a similar system with a throttle. So if you've ever seen a motorcycle or ride like an ATV before, they have a little throttle that you can, turn, and this tells your bike that you want to go forward, right? It can also tell your bike, oh, I want to go backwards, I want to go reverse. So you have a little throttle, and this will be called our input device. Now, no matter whichever electric vehicle that you're working on, right? Either it's the electric bike, electric skateboard, or the one wheel, they're all going to have these same components, which is really cool. Even if you think of it like an electric vehicle like a Tesla, it has these exact same components in them, just on a lot bigger scale, right? Yeah, and they're all the exact same. So they all use just these 4 simple components, and from those 4 simple components, we have an electric bike. Right, so here's an example of a motor on an electric bike. So this is called a hub motor, and it's embedded on your bike. This could be an example for a battery. I'll also go into more in depth on a battery since you need to choose the configuration for it and start buying stuff for it. this can be an example for a throttle for our bike. And this can be an example of a motor controller. Alright, cool. And obviously, you know, they come in a lot of different form factors. So this might be the motor for our bike, right? But there's also motors for, you know, our one wheel and our skateboard. So here is a motor for our skateboard. Hello. Alright, so that's pretty much it. So do we have any questions on basics of electric vehicles? Or are we good? I think we're good, right? Alright, cool. So other than that, so your first task assigned to you this week, if you're on the bike team, I don't think you had your meeting yet, but the other teams did. So your first task was to create, or pretty much choose a configuration of batteries that you need to use. So if you see this picture right here, these are battery cells that are called lithium-ion batteries. And we use them in electric vehicles because they're honestly really great. So they have a really high discharge, which means we can dump a lot of current. They also have a pretty high capacity for what it is. So it has high energy to mass ratio, which is really important when you're making any vehicle. So in general, we use lithium-ion batteries. So these ones in specific, and the ones that we're probably going to use, are called 18650 batteries, which just describes the dimension of the battery, which is 18 times 65 millimeters. And they sort of look like this. Alright, cool. And again, for the reasons that we use them, they're high discharge and pretty high capacity. Alright, so to give some specifications for these batteries, each battery cell runs at approximately 3.7 volts, which is their nominal voltage. That means normally they are 3.7 volts, but they can range anywhere from 3.4 volts and even lower to 4.2. Usually you don't want to go any lower than 3.4 volts or else your battery has a chance of dying pretty much. They also have, again, a pretty high discharge of 15 amps, which is a lot of current. So if you do the math to get the power, which will just be equal to the voltage times the current, 3.7 volts times 15 amps, each one of these cells can output around maybe 50 watts, which is quite a bit. Alright, so to specify the battery for our use case, we pretty much have to look at the motor that we're using, because that's the thing that's mainly turning the electrical energy into kinetic energy, right? So in Canada, we have a rule that states for electric bikes, and this is kind of what we're going to keep to for all our electric vehicles, that our max motor output will be 500 watts. So for electric bikes, it's 500 watts. Yeah, but for different configurations, such as a skateboard, we might have a different wattage that we might use. So here you see two smaller motors instead of one huge motor. So each one of these will instead be at 250 watts. And since they both run at 250 watts, we have to run 500 watts, right, times 2. All right, cool. So we want to specify our battery to the motor that we're using, pretty much. So how do we do this? Well, if we look back, we have our power is equal to voltage times our current. All right. And we want around 500 watts of power. And we need to find out how much voltage and current that we want to have, pretty much. So you can play around a lot with voltages and currents and pretty much find any like specification. But you know, as you go too much or too little voltage, then you kind of get unrealistic results, right? So you want somewhere in the middle. So a lot of people have experimented with different like battery packs and battery cell configurations, and they found out around 36 volts works best, right? And then we can find the current using math. So at 36 volts, our current will be around 14 amps. 14 amps. right? And that's right in the specification range of these lithium-ion battery cells. So that's really good. But how do we get this 36 volts, right? So if you remember like any electronic classes that you might have had, if you add two batteries in series, you actually add their voltages together, right? So to get the 36 volts, if each one of these batteries are running at approximately 3.7 volts, right? If I add two in series, so here I'm adding two in series, instead of having this 3.7 volts, I will have 7.4 volts at the end, right? And then I can add even more cells in series. And this is how most people and most like electric vehicle manufacturers make these batteries. And this is how Tesla does it too, except they do it with like hundreds of these batteries. So here I'm combining another pack of cells. So after adding 3 batteries, I should have 11.1 volts. After adding 4, I should have 14.8, and so on and so forth. So to get around 36 volts, I would need 10 of these lithium-ion battery cells. So here is 10, right? And at the very end, by adding all of these in series, I'm going to have 36 volts, all right? Now another thing that we have to take in consideration is range as well. So we want our electric vehicles to be able to go a lot of places. So something I forgot to mention is that each one of these cells can also have 3 amp hours usually, which just means it can discharge 3 amps for 1 hour. Hello. So it can discharge 3 amps for 1 hour, right? So usually this would get you around 10 kilometers of range from, I guess, just a lot of testing and experience. So 10 kilometers isn't too much. So what people usually do is add even more range by adding cells in parallel. So if you remember, adding cells in series adds the voltages, right? Adding cells in parallel will add the current pretty much. So instead of having this 15 amp output, we can have a maximum of 30 amps of output, which is a lot more current, which means we can, go faster if our motor allowed it, right? But this also increases the range. So instead of 3 amp hours, we have 6 amp hour batteries, which means we can go double the range pretty much. So if I could go 10 kilometers before, now I can go 20 kilometers. And what we have to do to make that happen is to pretty much add another set of cells in parallel. So here's my series cells. If I add cells in parallel, something like this. Let me get rid of these minuses. Let's see if that looks better. So if I add my cells in parallel and I start attaching these in parallel, now I made a complete battery pack. All right. So we call this battery configuration 10S2P for 10 battery cells in series and 2 battery cells in parallel with each series pair. And this gives us a total of 20 batteries, right? 20 cells. And now we have a super big battery pack that can output 37 volts and meet the specifications of our motor. So it can run pretty much everything. Is that good? Yeah. All right, cool. All right, so let me give you a sec to take that in. Yeah, does anyone have questions? Or are we all good? It makes sense? Nice. Yeah, so it's kind of some like basic math. We just keep adding more stuff and then we get more stuff as output. All right, after that, right, there's another thing that you have to purchase, and we call it the battery management system. So, there's no way of us regulating these batteries as of right now, like as they are. So it's really important that we add external circuitry to, I guess, make sure that it doesn't blow up pretty much, right? So, all these batteries running, let's say you ride your skateboard or your bike or your one wheel a couple of times, all these batteries will discharge some, recharge some, and at the end you might have batteries that are like half depleted. Like this one, you might have batteries that are still 80%. You still have batteries that could be 20%, and there's no real like protection against these batteries. And the more that you use it, the more they could go out of balance. So we use something called a battery management system. system, or a BMS, so that we're able to pretty much make sure that the charge of each cell is proper, right? This also does a lot of things like add over current protection. It does things like add over voltage protection. It can also add stuff like under voltage protection,
short circuit, which is typically overcurrent.
Short circuits, temperature protection. Pretty much, it's there to make sure that your battery doesn't blow up. Because as of right now, this is pretty much like a huge bomb. Temperature protection, right? And we don't want anything to blow up, so we add this circuit protection. I can spell. All right, cool. So how do we attach this battery management system? Well, it comes with a lot of leads, and I guess the explanation for how the actual circuitry is a bit more complex. But all you really need to know is that you connect a wire to each one of these sides of the batteries, like this. And
I'll use a different color.
Yeah, I'll use a different color. You're right. So you add each lead to like the positive side of a battery. Right? And what this does is ensures that each battery charges properly. So when you plug your electric vehicle into the charger, let's say this battery charges all the way to full, but this one still isn't quite there yet, it's going to stop charging this battery and continue charging this battery. So it can also reach the same voltage as this battery. And then everyone's happy. Yay.
We should also go over passive versus active balancing.
No, it's fine. I think that's too much.
Because that's what almost caused me to fall.
No, I think it's fine.
All
right, so that's pretty much what you need buy. You need buy the lithium-ion cells, and you need buy the battery management system, and anything else that can go in the battery pack. So for this battery, we can't just like attach it like Legos. We usually spot weld nickel strips, so we make a good connection between them. And we also can't just solder the lithium-ion cells because they are really bad at taking high temperatures. So we want to spot weld them instead so that you have an instantaneous high temperature and you don't damage the cells. So some things that you can look for, I think there's a list of things to buy in the workshop details, so I think you can look at that. But things like nickel strips, extra wires, thick gauge wires, the actual cells, the BMS, those are things that you're going to buy. So just go to your project lead once you figured out what you want, and you're going to aim for a 10S2P configuration for pretty much all the electric vehicles. One wheel might be a bit different, but we'll talk about that a bit later. So for now, for bike and skateboard, you can aim for a 10S2P battery. All right, cool. So that's it about the battery. So you have another task as well. So this is pretty much your first task. Go online and try to buy these batteries and try to meet these specifications that are here too, like 3 amp hours, 3.7 volts, 15 amps. All right, cool. So other than that, we also have to talk about the motor controller, right?
Sharon, can I ask a question?
Yep.
Can you explain, is the BMS a physical component or is it more chemical component?
I'm not too sure what she said.
The BMS, battery management system, is it like a physical component?
The echo in the room is pretty bad.
Yeah, I think what you're asking is is it external? Yeah, it's an external circuit that you would buy with your battery. So usually they're specified for if it's a 10S battery, you would buy a 10S BMS. Cool? Sound good? All right, I think that's good. All right, cool. I'm gonna go over, so as I said, that goes over the battery. So we want to buy these kind of quick because shipping might take a month or two. So by the time we buy it now, we'll have it in 2 months or 1 month, and then we can assemble it together when the time comes. So you guys get to pretty much spot weld the battery together, which is really cool, and solder some wires to it pretty much. All right, other than that, we also have the motor controller. So you're gonna start on the schematic for it. I'm not too sure how much you guys want to do, so we can go really low level for the motor controller, or you can kind of stay at a pretty high level of understanding and still use it. It's really up to your team. But I'm going to go, I guess, a bit high level on the motor controller. So this is kind of the general explanation. So like any kind of like circuitry, we have an input, and pretty much like any function that we have in like math as well. We have some input, we have some output, and in the middle we have some processing that's going to happen, right? And this processing is pretty important for, you know, translating our input into an output, right? So it's like kind of like a classic block diagram. Does that make a square? Nice. So in our case, whenever we, you know, pull back on the throttle of our bike, right, we want to go forward. So in this case, our input will be our throttle, right? And our throttle will give out an analog signal. All right, and then there's some processing in the middle that's going to do that. And from this analog signal, we're going to have some output, right? And obviously, our output will be making our motor spin, so motor spinning. So in the middle, we have to do some processing to be able to, I guess, get everything to work. So one of the first stages of translating the input into an output is first we have our MCU, or our microcontroller. All right. So what a microcontroller is pretty much a small computer that can do a lot of calculations for us, pretty much. So, you know, all the complex algorithms and stuff like that, all the signals that we have to process, it goes through the MCU, and the MCU can pretty much do these signals and give them out. So it takes inputs and also gives out outputs. So what it's going to do is it's going to take the throttle input and determine what to do with it. So if I want to go backwards with the throttle going backwards, the MCU will figure out how to do that. If the throttle wants us to go forwards at like 20% speed, the MCU will have the algorithm to be able to do that. All right, so a lot of the complex algorithms, guess what? We don't have to worry about, because we are electrical. So a lot of the algorithms that we have to do is part of the firmware team. All right. Now the MCU will communicate with a circuit IC, or integrated circuit. That's called a motor driver. All right. Motor driver. So pretty much in between the MCU and the motor, right, we need some sort of protection, like some sort of transient protection. As well, the MCU works at a pretty low voltage level. It can't work at 33 volts or 36 volts like our entire circuit does. It can only work at a lower voltage level, like 3.3 volts. So our MCU somehow needs to step up the signals that it has, so it works with that 36 volts that we're working with. So the motor driver is able to translate the signals that are relatively weak from the MCU. So here are like weak signals, right? And it needs to make it a lot stronger, so that we can actually use it pretty much. All right. The motor driver also adds, you know, basic circuit protection for us as well, which is really important, like overcurrent, under voltage, temperature protection, so on and so forth. So there's a lot of protection on the circuit from the motor driver. All right, cool. And now we come to our last stage, right? So here we have a stage of transistors, all right? So they're NMOS transistors. I can't fit it. All right, and what the transistors do, right? If you know, all they do is turn on and off, right? Now there's a specific pattern that the transistors need to be able to move a motor, and it requires a bunch of complex algorithms that you don't really have to worry too much about, since firmware will do most of it. As well, the motor controller also deals with some of these complex algorithms. So in the end, all you have to do is wire it up properly, and then everything else is kind of handled for you. All right. So from the microcontroller, first we have to boost the signals and add protection to our circuit. Then we have to actually be able to turn on and off specific signals. And from there, we get a motor to spin pretty much. All right, so this is the main circuit that you guys will be making. This black box right here. So you're going to go from schematic design to PCB design to actually having it in hand and soldering it, wherever that needs to be soldered. Does that make sense? All right, cool. And that's pretty much the, I guess, low level, kind of mid level of what we need to do. And yeah, I think as you work on it and like get more information, you'll kind of understand more about how everything interacts with each other. But that's the main gist of it. All right, let me see what else I need to do. Oh, okay. I guess that's it. All right. So that's pretty much it for, I guess, the like lecture material. My bad, it's kind of boring, but it's kind of what you have to go through so you can make these type of things. So again, I said you can go high level and low level on this. So the low level is pretty much the schematic design, making the PCB for it all, having the ICs. And I guess the higher level is just buying one of these units, buying one of these motor controllers, and then implementing it in our electric skateboard, electric bike, one wheel, whatever you have. So it's really up to you in the end where you spend your money on and what you want to do. For a lot of these circuits, they're a bit finicky. So if you go the low level route and you want to learn a lot about circuit design and stuff like that, we do have like a lot of backup motor controllers that you're able to use. So even if your entire thing doesn't work, it doesn't matter. In the end, like you just use it as a learning experience, and we'll have pretty much these backup motor drivers that we can use in the end, our motor controllers. That's pretty much it, I think, for the online people. Yeah. So thanks for coming, and I'll put the recording on YouTube or something as well. So yeah, thanks for coming. Okay. Cool. So for those of you in person, we also have a couple schematics that we want to build. So one of them is, it's up to you if you want to build it or not. It doesn't really matter. So one of them is the anti-spark circuit. So I kind of went through this whole spiel of, oh, this is how our motor controller works, but we need like an on and off button. So this is a circuit that acts as our on and off button. So we're working with like really high like currents and really high voltages. So unfortunately we can't just like turn a switch and then it turns on. So this is the circuit that we have, and you can also build it if you want in person. If not, there's also another circuit. There's also another circuit that's a bit simpler. This is like a buck converter circuit. So what it does is it steps down our 36 volts to our 3.3 volts on our microcontroller, which I talked about before. So if you want to build it, you can, and we have the stuff. If not, that's pretty much it. Do you guys want to build it? Yeah? All right, cool. So you can probably get into groups. I think there's only 4 of you, so maybe you just build it all together. It shouldn't take too long. Do you have one specific one you want to focus on?
They should do both because ultimately they'll probably need to design both.
Okay, let's do this one first. So the schematic, I'll give you the schematic, and then pretty much you guys can design it yourselves. Yeah, so I guess the initial plan was like, you learn schematic, reading schematics pretty much, but no one came. But it's all good. Yeah, thank you for coming. I really appreciate it. So this is the schematic you can build first. So all the stuff is there. I'm gonna put on some jams, and you guys can work all together and do it.
So you want me to? I can probably just explain what this is first of all. So you're excited?
Turn it on. Turn it off. We'll show them an example. What's good? What's good, Blade?
See, that's what I mean. They just did it.
What? What did we do?
I was saying because of like my class, my class is like 90% guys. I have to like
Oh.
He doesn't even know how to do it.
I don't even know how to do it. I just do it because he does it.
No, it was so weird. I didn't like
Okay, but now you're good at it, so it's all good. No.
Let's do this.
I haven't had
No. All right, go build circuit. Why are you tired?
Just went to the gym and I'm exhausted.
So this is called like I guess it's explained.
Is this the reference voltage or are we using the common voltage?
This is the common.
So this is basically your battery positive, battery negative. And this is your board, your remote, the positive and the remote. So the problem is, motor controllers have a lot of capacitors, which will basically mean the moment you plug it in, a whole bunch of current is going to be dumped in the controller. So sometimes people don't like that.
Sometimes.
Sometimes it's kind of scary and it's kind of experience. But this also has some power switch. So it's hard to find power switches that are made for high current because the kind of contacts, they spark when you like turn them on and off, and after you heat it switches, they eventually weld together. Which is not good. That's why you know light switches, how they kind of click. That's to help you mitigate that. But in this case, we're dealing with like what? Current electrical around 30, 50 amps, maybe? Which is not good. It's instantaneous, but it's not good. So that's like that. So that's what this is. So again, if you don't know a MOSFET is basically a whole So we can turn this MOSFET to say, okay, is it going to be shorted or is it